Welcome to this edition of the OnTrack Whiteboard video series. My name's Ben Jordan, and today I'm up to part 2 of a multi-part series on multiboard PCB design. And what I want to talk to you about today is connectors and connection. And really, for the most part, connectors. It's a very important thing. If you're designing a multi-board system, at some point you have to make a few decisions about what kinds of connectors you're going to use, what kind of connectivity, and there's a few factors in deciding which connector mechanism to go for, which sort of solution to go for. So I want to walk through a few of these and what are some of the attributes that you really need to pay attention to so that you can avoid DFM and DFA problems in your final assembly. So to start with, there's broadly 4 categories of interconnect solution for multi-board systems design. There's typical board-to-board connectors, and these things fall into this category, such as these hermaphroditic connectors or headers and header sockets and plugs and sockets of various different kinds. And a subset of that would be direct soldered, which I'll come to a bit later. And then we have board to cable or board to wire. And this is really only part of a multi-board system in the sense that you would have a cable harness or some wires going from one board to another. For example, from your power supply unit, which may be an off-the-shelf module that you acquire from somewhere else, to your main printed circuit board. So there's different considerations for different ones. And then also as kind of a subset of board-to-board interconnect, we have card edge connectors, and there's different pros and cons to each of these. So looking at board-to-board connectors, so here I'm talking about the pin header and header socket kind of interface, and there's many different kinds of these, but they're pretty common and fairly low cost. They're pretty much de facto standard in the industry, but there's some trade-offs to using them. They're not necessarily designed for very high speed, for example, and you can put some reasonably high speed through them, but you need to take up additional pins for ground return paths for signal integrity purposes if you're going to do that. And there is a practical limit given frequency, performance and impedance to these as a solution. So you need to decide, are you dealing with very high signal edge rates, or can you get away with a lower cost connector that's not necessarily made for high speed? And coming back to that, I mentioned the number of pins needed. So the first big trade-off is pin count. You have a physical constraint of your actual assembly, and obviously there's only such a size connector that you can put into that physical space. So can you get the number of signals you need in that space, along with appropriate ground return paths and power supply handling? If you're going to ship heavy currents, if you're going to connect, is a better word, power supply, power and ground through a connector from a baseboard to a daughterboard, for example, and that daughterboard needs a reasonable amount of current or power delivered to it, then one of the most important characteristics of the connector is its current handling capacity, and that's usually specified by the manufacturer in amps per pin. Now, just as an example, I'm going to switch over to a data sheet for a fairly standard kind of pin header product now. This particular one is from Samtec, but many manufacturers make the same exact kind of product. For example, TE Connectivity, Amphenol, Hyrose, Harwin, many reputable manufacturers out there for this kind of product. So if we look at this particular data sheet, this is a really good one because it gives us a whole list of specifications down the side, and in a very clear box inset, it shows the current rating per pin. Now the example I'm giving you here is for a TSW series product. That's the Samtec part number prefix for this one. But you'll note that the current handling is given as 2 positions powered, so it's a power and a ground return. But it's different depending on the mating connector. So this is a pin header, and it's mated to a female header or socket, a plug and a socket, and it depends on which socket you're using. Some of them have thinner contacts and different contact edge plating, and that has a profound effect on the current handling capacity. So the SNT socket, for example, only gives you 4.3 amps per pin. It's still actually pretty generous. Whereas the SSQ in the middle of that table gives you 6.3 amps per pin. So maybe you can actually choose both the header and the socket together, knowing how much current handling capacity you need overall. And that could free up some pins for signals on the same connection. So that's the first kind of trade-off, is how many pins can you get away with and what kind of power requirements are there. Next, let's talk about duty cycle, because the other thing with multi-board systems is one reason to do a multi-board system is to fit the whole thing into a smaller enclosure to get more electronics into the right shape. And if that's the case, where you're just connecting everything together and then shipping it off and it never opens again or is touched, then you don't need a very high duty cycle. So you want to look at the manufacturer's recommended duty cycle limits for the connector. Now, usually there's a pretty broad margin on these, but it's about what they agree to be held accountable to. So if you're going to produce something more like a card edge connector based peripheral that's going to be inserted and removed several times, then that might be more of a consideration as to duty cycle. So by duty cycle, I mean how many times can you insert and de-insert the assembly before the contacts wear out and become unreliable. I mentioned that's probably even more of a concern for a card edge connector. And so going on to card edge connectors, let's talk about those for a minute. So in a card edge connector, we have a plastic socket that's got some spring-loaded terminals on either side. It has an advantage of being fairly high density, and these are usually specified for industry standards like PCI, PCIe, Q7, and there's many other standards that are basically designed for computer motherboards and their peripherals, or high-speed digital assemblies, and they may define good grounding and differential pair signaling, so you get fairly good throughput. So for example, PCIe connectors with the right designed card edge, you can usually reliably get 5.8 or more gigabits per second on each pair. But something to look out for here is these products may be in storage for some time before they're actually inserted. And so there's a design for manufacturing issue here where the actual printed circuit board, while you could use bare copper contacts, usually the standards require that you have hard gold plating on your contacts on the board edge connector. So we call these the gold fingers. So that adds a little bit of cost to your actual PCB fabrication, but it may be less than the cost of a otherwise what would be a connector anyway. But it just means you have to specify a little more in your manufacturing documentation what you expect here. You need solder mask openings to expose those gold fingers, and you need extra milling and machining to do the chamfered edge of the card edge connector that's in there. So there's just a few things to do with design for manufacturing if you're going to go the card edge route. The other advantage of the gold contacts is they're less likely to corrode, and when you get the physical insertion happening, any corrosion, thin corrosion that may be there on the contacts is wiped away. So you get a pretty good connection. So it's generally pretty pretty reliable. Again, only really suitable if you want something mounted at right angles to the baseboard. Another kind of connector, which is becoming more popular, is the hermaphroditic connector. And I've got a pretty basic drawing I've attempted to do of one of these here. But again, I'll switch over to this TE connectivity data sheet that shows a pretty good diagram of how hermaphroditic connectors actually work. And we have the exact same part, but when you flip it over, it mates with the exact same part. So you have two of the exact same manufacturer part number from TE, and it's mounted on both boards, and one of them's upside down. And so this is really good for your bill of materials because you can buy more of the same part and therefore get a better price, and it can make manufacturing fairly straightforward. And they work really well, and many of these are available with good ground return mechanisms for high-speed signaling as well. There's one gotcha that you've got to look out for, and this comes back to your CAD library for the footprints and 3D models of this part. And that is that in the data sheet they will specify, I'll choose a different colored pen here, in the data sheet they'll specify that pin 1, for example, may be here, and that same position 1, if we flip it over to the other side, and that's hiding down there on the opposite corner of this connector, right? Because if you turn the thing upside down and flip it around, pin 1 ends up over there. So when these mate together in the final assembly, pin 1 actually connects to pin 2 on the other side. So there's two different ways you can deal with that. One is, in your multi-board schematics, you can just accept the fact that you're going to have in the connectivity manager, or connection manager in our case, you're going to have on one side, one board, pin 1 is going to connect to pin 2 on the other board, and 2 is going to connect to 1, 3 is going to connect to 4, and 4 is going to connect to 3, and so on. It's going to be mirrored. The pin numbering will be mirrored. And you just have to accept that the electrical rule checker, you're going to have to enable it to allow those mirrored connections. Or the other way to do it is you create two footprints for the same library component, kind of like a variant, if you will, and you have the same schematic symbol but two footprints, and you can choose which footprint to place based on if it's mounted on the top of a board or if it's mounted on the bottom and mirrored, in which case you mirror the pad numbering or pad designators in your footprint to reflect the actual connectivity that's going to be in the final multi-board assembly. Both have pros and cons, both have risks, but you need to be aware of it as the designer so that you don't run into troubles with design for assembly. And while I'm on the topic of pin numbering, you actually have the same scenario occur even with multi-row pin headers and sockets. You need to be aware that on the data sheet you're looking at a top-down view of the connector. So here's the male connector, and this would be pin 1 traditionally in the top left, and we might go 2, 3, 4, 5, 6, 7, 8, 9, 10. And the socket, it's awfully tempting to do the same pin numbering scheme. But again, bear in mind when this is on another board and those two are interfaced together, this should be pin 1 because that's going to mate with that pin, and that socket's going to mate with that pin. It's going to be mirrored. So make this 1 and this 10. And this will be 5 and this will be 6. And so again, this comes down to your CAD library, and you need to number these correctly with forethought of how these are actually going to be used in a multi-board assembly. On the subject still of design for assembly, one more issue to look out for, and again this is something that should be specified in the manufacturer data sheet, and that is operating temperature range. So operating temperature range is operating temperature range, but it gives you an idea of what the maximum temperature withstanding over an extended period is of the insulation material of the connector. And in addition to that, good manufacturers will either give you a soldering reflow profile for your assembly for the soldering oven. So you know what's the maximum temperature this connector can be subjected to during assembly for soldering purposes, or they'll tell you what the material is in the insulator. In the case of this Samtec header, it's the TSW I was looking at is black glass filled polyester. So polyester is a reasonably high temp plastic as it is, but with the black glass, it's black, but with the glass fiber filling or glass crystal filling, it actually gives it a higher temperature tolerance and thermal mass for going through reflow. So I know that's going to work pretty well for reflow soldering. It's awfully tempting sometimes to find an alternative source of these connectors on the grey market, and they're a lot cheaper. But if you do that, be warned, you need to get a few of them into a lab first and do some flame testing, do some testing with a hot air gun, and do some testing with some power supplies and loads and multimeters to make sure that their contact resistance isn't going to be a problem and that they can actually meet your current handling requirements. Sometimes the only way to get the data you need is to actually test it. Otherwise, you could find yourself with a pile of goo coming out the other end of the soldering reflow oven, and I've seen that happen. It's not pretty, and it makes people go home crying. So you don't want that. So make sure you know what the temperature range is, and if possible, what's the material for the insulator of the connector. Just one final thing, talking about, two final things actually, talking about board to cable and wire. I've got an image here of a wire soldering terminal or post, and these aren't used very much anymore. They're kind of a little bit expensive to work with because they may need some hand assembly of the final system. But if you are doing those, there is an industry standard for these and for all other kinds of connectivity to specify what the quality should be. If your design is IPC Class 1, that is a low-cost, mass-produced electronics, it doesn't have to be reliable, or Class 2, moderate complexity designs, or Class 3, sort of high reliability products like military, aerospace, each have different requirements for soldering quality for all these different kinds of interfaces. And those requirements are laid out very clearly with good full color images of what the joints should ultimately look like in IPC 610. I think we're up to revision G now, but if you're concerned about quality and reliability in your design for assembly process, you should definitely, in your documentation for manufacturing, refer to IPC 610 and call it out as the standard to be met for the quality of and reliability of the solder joints of your interconnects for board-to-board assemblies. And just one last thing, I will mention direct soldered. When I say direct soldered, I mean there are scenarios where one PCB and another PCB are actually soldered directly without a connector to each other. And examples of this would be, for example, castellated. That's the word castle, and it's not castellated. Let me spell it correctly for you. It's castellated. Castellated modules. Now, castellated modules are also referred to in IPC 610G for reliability and quality of solder joints. And castellated modules is when you have one PCB soldered directly on top of another with solder joints around the outside edges. And we're seeing this increasingly, especially with IoT related projects. There's a lot of little Wi-Fi connectivity modules like the ESP8266 or ESP32 modules out there, or Photon, Spark, and other little modules that people are using now, because it allows you to get connected to something without having to go through all the headache of the RF design yourself. So these are becoming more and more popular. So in an upcoming episode, I will also talk about, in addition to signal and power integrity, we'll talk about how to do castellated modules for multi-board design, and various other things to look forward to in a future episode. That's all I have for you today. It's Ben Jordan again. If you really liked this video, if you found it at all useful, or if you have questions, please comment below. If you liked it, subscribe, follow us on Twitter, follow us on Facebook. We'd really love to hear from you. And if there's anything you'd like me to cover in this series, particularly related to multi-board design and connectivity management, let me know. And this has been OnTrack Whiteboard Series video. Thanks for watching.